Hello, everyone, and welcome to the Artificial Intelligence in Search for Life discussion panel that is conducted as a part of Life in Space 2022 conference held by the Polish Astrobiology Society. I'm Nicola from Polish Astrobiology Society, and I'm going to be moderating today's panel. We're going to discuss what do we mean by searching for life, what are we searching for, how do we do it, and how can we use artificial intelligence algorithms to help ourselves with that. We're pleased to host 4 exquisite guests tonight. Welcome. I'm going to call your names in alphabetical order, and once I do, please tell us your affiliation and a little bit about yourself, as well as your current research area. So let's start with Ewa Borowska.
Hello, I'm Ewa. Hello, everyone. I'm from University of Warsaw and Extremo Technologies company. Basically, I'm working on extremophiles from volcanic grounds. Mostly it's microalgae.
Okay, thank you very much. Let's go now to Łukasz Kidziński.
I'm Łukasz Kidziński. I've been a researcher at Stanford for about 6 years now, and for the last 2 years, I've been working at a company called Clario, which I joined after acquisition of my startup, focusing on automation of processes in medical imaging, particularly in clinical trials.
Okay, thank you, Łukasz. And Karol Majek, your turn.
Thank you. I'm currently working as senior computer vision researcher at TensorFlight, analyzing images from the ground, street level imagery, and aerial images.
Okay, thank you, Karol. And last but not least, Janusz Petkowski.
Welcome, everybody. It's a great pleasure to be here, and I hope that we are going to have a great discussion and very interesting one. My name is Janusz Petkowski. I am generally a research affiliate at MIT in the Department of Earth, Atmospheric and Planetary Sciences, and I work on astrobiology. This is essentially my main topic of research.
Thank you, Janusz. That was inspiring, so thank you all for those brief introductions. I'd like to start tonight's panel with not so obvious and not so naive question, which is, what is life? What I mean by that is, how do we define life, both on Earth and alien-like? And is there even a distinction? So, Janusz, this one is for you.
Thank you very much. Well, this might sound like a simple question, but it is not actually. And frankly, there is no one definition of life that everybody or every scientist would agree on. So essentially, the NASA definition is that this is a sort of a self-sustaining complex chemical mechanism or entity that is capable of Darwinian evolution. But is this actually a definition that everybody would agree on? Absolutely not. I would actually argue that we do not need to define life to actually look for it. And this might sound like a pretty controversial statement, but I hope that during this panel I will be able to convince you and the audience, everybody, that we actually do not need to define life to actually look for it.
Okay, so why would you say that? Tell us.
Why would I say that? It's because essentially we have to ask ourselves, if we search for life, what do we actually look for? Yes, what does it mean to search for life? And essentially what we are trying to find, something that doesn't fit. We are trying to find some sort of anomaly. We more or less understand how the planetary environment in various places works, how the planets works, how the geology of a planet works. So if we actually detect something that doesn't fit, or it's like, for example, complex in its, like, for example, some complex chemistry, then this actually opens a possibility that this might actually be a product of life or some manifestation of life. So what do we actually, for example, look for? I mean, we look for, or what those anomalies could be. In terms of chemistry, they could be, for example, some sort of biosignature gases, some gases in the atmosphere that we cannot really explain by any known chemical mechanisms or chemical processes on the planet. But we also look for example, complex organic chemistry. Yes, if we actually land a rover on Mars or other planets, we could look for organic chemistry and see how complex the organic molecules that we detect really are. And the more complex organic chemistry we detect, the more likely the origin of those molecules, the more likely it is that the origin of those molecules could be life.
Yeah, I completely agree. And I'm very glad you mentioned biosignatures, because that brings me to another question, which is, what exactly are biosignatures? So Eva, could you tell us?
Thank you. So if we are talking about biosignatures, we are talking about remnants, or maybe what I'm working on is preserved substances, which are mostly in the rocks, because we are, of course, looking for a life on other planets or exoplanets. So I'm not talking now about gases, but exactly about chemical compounds like carbon compounds or sulfur compounds inside the rocks. And what we are looking on now on Mars, on or other moons, yes, it's exactly the chemical compounds which are remnants after the maybe previous life.
Okay, thank you. So to finalize the introduction to astrobiology, let's add another question to that list, which is, how do we look for life? Meaning, what tools do we actually use? So I like to ask our astrobiology camp here. So Janusz, Eva. So Janusz, can you start?
Yes, of course. It actually depends where we are attempting this search, because it will be very different if we actually look for life in our own solar system, or if we actually try to find life outside of our solar system on exoplanets far, far away, many light years away. So if we are actually looking for life or signs of life on exoplanets, so light years away from our own solar system, we have to rely on the atmospheric biosignature gases. So essentially, we hope to actually find some signatures of gases that do not fit our understanding of the atmospheric processes, photochemistry, or geology of the planet. This is mostly done by the so-called transmission spectroscopy. So we hope to actually collect the light from the star as it is filtered through the atmosphere of the planet. And then from that spectrum, we hope to identify the constituents of the atmosphere of the planet. And among the gases that are regular, like, for example, carbon dioxide or some other gases, we hope to find those rare instances of gases that we cannot really easily explain by non-biological processes, like, for example, oxygen on Earth. And if we look for life in our own solar system, we can actually go there. So we can actually develop much more sophisticated instrumentation and land rovers on Mars, for example, and try to look, for example, for this complex organic chemistry that I mentioned.
Eva, do you use the same kind of tools or something else?
Yes, I totally agree with Janusz, but what I would like to add also, it's what we are researching on Earth, on analogs. So what we are using is, for example, gas chromatography or mass spectrometry. It's like nowadays it's most popular. And what I'm using also, it's isotopes. So isotopes like carbon or sulfur, or isotopes of metals. We can adapt the tools for looking what was the remnants in the previous life on Earth, because if we are talking about Archean, it's the mostly probable past life on Earth. So we can compare it, for example, to places on Mars as well. So what I'm working on, it's sulfides and sulfur, and actually isotopes, which you can tag and check if any other chemical organic compounds are the remnants inside the rocks.
Okay, great. Thank you, guys. So let's move to the introduction to our second part, which is, broadly speaking, artificial intelligence algorithms like deep learning. So say we have those huge data sets and images from all our scientific equipment. Łukasz, could you explain to us how could we use AI and what AI methods could be useful to analyze those? I understand you work with medical data, so you must be also looking for similarities. Tell us about that.
Right, like in my work, most of the work is actually concentrated on finding patterns in the data, and there's usually lots of noise in whatever you collect, especially in time series analysis or in imaging. Their images that you're dealing with are subject to lots and lots of noise, and methods that we're trying to use effectively are trying to narrow down a huge matrix of pixels into a small vector of important features of an image. And that's used everywhere in medical imaging, but also like in any other field where computer vision is used. Essentially, what we do is we narrow down data from a large matrix to a small vector. But then more broadly on artificial intelligence, I think what comes to my mind as applications of AI in space discovery and in looking for life, this example of the space rover or the planetary rover, where we need to build a robot basically to navigate around the planet to collect most important specimens from the planet. Those are tasks that are tackled right now with reinforcement learning in AI. So lots of robotics actually relies on techniques where we build some kind of model of what we're exploring. We are running our AI agents to simulate potential control of those robots, and we optimize certain objective functions where the objective here could be to find some traces of life. So there are tons of applications of the current trends in AI in what you already discussed in this panel.
Okay, thank you. So Carol, as I understand, you deal with computer vision. So can we use computer vision methods to process some multispectral images like those we can obtain from satellites instead of standard RGB data?
We can use standard state-of-the-art computer vision models, which are used mainly for analysis of RGB images from, let's say, what we can see around us. Yes, so most of the networks are trained on the data where you can see cars, people, streets, like trees, everything what is on Earth. And if we want to switch domain into, let's say, for the medical use, or where we don't have free channels, or we want to explore how to use those models for using multiple channels from multispectral imagery, we just need to increase the number of input layers for such a model, and then we need to retrain it. We can't use models which are already trained. We need to start from scratch, but for this specific use, we can use unlabeled data to pre-train our model on a, let's say, a large set without any labels from humans. So it can be just a raw imagery from multiple sources, just to train the model to make it able to extract features, the embeddings, those vectors from images, to transform the input image into a feature space, and then we can compare those images using these vectors to find similarities or to find outliers. Yeah.
So we could potentially train them to find similarities like biosignatures, I understand.
I think yes. I think we could use such approach to find such outliers, but we need to be sure that it's different from our training set. So if it would be beneficial to have such images, to have mixed images in our training data, yeah, even without labels, but it would be good to have.
So we would have to create random anomalies, like Janusz said, because we are looking essentially for anomalies as some sort of training set, I guess, to give it an idea of what we were looking for.
You know, the best is to have already the life on other planets, yeah, and have it to just check to validate our model, yeah, the approach. But of course, we don't have it yet.
That's the dream.
Yeah, that's it. That's the goal.
Okay.
Yeah.
So one of the methods to find similarities, from what I understand, is dimensionality reduction. Łukasz, could you explain us what is meant by that?
Right, I think it actually is aligned with what Carol was explaining. So essentially, whenever we have a large set of data, we can extract the most important features from this data, or like similarities between images, or similarities between different data sets as a set of features. And In lots of applications, that's essentially what we're trying to do. So whenever you have a big computer tomography scan with lots of voxels, lots of pixels, what you're interested in is whether there's cancer or not. Like you're interested in some binary output, even though you have a large set of data, even for one patient, and then you have hundreds or thousands of patients. And in the context of looking for life, I think the kind of inverse approach might be useful. So you could try to look for similarities all over the place and like try to find patterns showing how different specimens from planets are similar to each other. But then what you're actually interested in are outliers. So you build a model of the reality. You kind of try to cover as much as you can, and whenever you see that something happens completely out of model, that's your hope for new life.
Great. So we're essentially looking for weird stuff, anomalies, and something that doesn't fit.
From my very narrow understanding of looking for life, I would expect that's kind of one of approaches.
Yeah, that's a pretty good definition, I'd say. Life is pretty weird compared to the rest of the universe, right? And rare from our perspective right now. So, okay, let's connect the dots. We have teams that are defining scientific goals, i.e. searching for biosignatures. We build our measuring equipment and send it to space. We design algorithms to analyze those data automatically. So let's discuss trends and problems. So Eva, from your perspective, what are the main trends and problems you could point from your scientific perspective?
So I would like to say something about Venus, because in last half year, let's say, we are analyzing with Janusz some maps of Venus, and we are comparing to Earth. And I can say that it's very difficult because still we have less data as we expected. So still we are on Earth, so we are comparing everything, every analog to Mars or Venus. So what is difficult in this point, what Karol and Łukasz are doing, they are comparing what is the anomalies, of course, yes. So what we can do now is looking on the map and search what is different between what is on Earth in the similar environment. So for me, it's difficult because for example, I'm not sure if that map, which was like it's based like I don't know, like 40 years, yes. We are comparing like maps nowadays. So this is very difficult, yes. So we have to look for the maps which were on Earth before. I don't know if Janusz agree with me, but this one actually it's very difficult, and this part. So about data, yes, we have not a lot of data about it.
Janusz, I mean the same question.
Yeah, absolutely. Excuse me. Absolutely, I agree. I mean, in a sense, this is a universal problem of all science, that there is no such thing as too much data. Yes, so we always can have more. What are the challenges for the field, for the search for life now, and what are going to be the challenges in the future are a little bit different things. Now we need more data. Let's say that we are going to have this data, then it's exactly where the work of Karol and Łukasz is going to come in to the forefront. Yes, because we, astronomers or scientists or astrobiologists, are going to just provide this constant stream and deluge of data towards people like Karol and Łukasz, and this is up to them to find these anomalies and patterns in the data. So I will give you an example. Yes. So now we have this wonderful space telescope, which is called JWST, James Webb Space Telescope. This telescope is going to generate an enormous amount of data, and eventually it is going to collect a lot of spectra from various atmospheres of various planets. Hopefully, we cross our fingers that most of these rocky planets actually have atmospheres, and we hope if they do, then this would make Łukasz's and Karol's work much more interesting, but at the same time much more messy and also much more maybe difficult. Yes, because what we would then expect from them and from the machine learning approaches and also artificial intelligence approaches and methods is to find these patterns, find some sort of plan, for the lack of better word, in this chaos of spectra. We would look for some signals that are faint, that might be an artifact or not. We would like to know that. And we then would like to ascribe this spectral information to specific chemicals in the atmospheres of these planets. And that is, of course, a challenge for the future. We now are in the process of collecting this information. We have first information about the composition of the atmosphere, pathosmears of exoplanets. Now we have need more data. In the future, we will just need to analyze and understand them.
I'm not sure whether Łukasz and Karol, do you feel the pressure you're under? Because there is a lot of pressure in the upcoming years from us scientists, so be prepared. So Łukasz, what would you say are the main trends and problems concerning automated analysis in computer vision and AI right now?
I think, yeah, maybe one thing that comes to my mind, and maybe it's not necessarily a trend, but like that's something that's missing in many places. So like there's a lot of work being generated in AI conferences and machine learning conferences. There's relatively less work on the intersections of fields, and the applied work still needs to catch up with there are amazing achievements I'm sure in both the space and life discovery work and in AI, but like the intersection, at least the one that I'm aware of, is relatively small. So I'm not sure what should happen in this direction. Like what happens in many fields is that whenever those massive data sets are generated, those data sets are then converted into a way into something that can be easily digested by ML and AI people, either through some competitions or through some kind of major papers that involve both sides. I'm not sure how it happens actually in your field, but I see that. So I'm personally from AI and ML, but like I got involved in biomechanics, and I see that those challenges and those shared data set is what drives the progress in actually both fields. So hopefully, yes, that's one of the trends that we'll see also here.
Okay, so we need intersections. So do you think we perhaps should make conferences for both AI and both astrobio people and just make them converse and think about what to do with the data sets? Or maybe we should like talk to students at the university level that this is something that is needed, because we do have two approaches, right? We have people who are more concentrated in this narrow field, which are specialists that are needed, and people who kind of manage all others, but there rarely are people that do both, right? It's not really easy.
Yeah, I think that's a great point, and I think there is a very positive trend happening now. So like around 5, 10, or 20 years ago, a lot of people with AI machine learning skills were kind of driven to join big finance companies, then later big ads generating companies like Google and Facebook and others. But now the new generation that I talk to, like people like myself and people at my university from Warsaw, I see that they're really driven by interesting problems to work on. Like they know that they don't need to just get a lot of money on Google and Facebook. They would rather get a decent salary at a company that drives the world forward. And the problems that you have here are definitely something that can get them excited. So I think like some kind of PR and marketing skills from your community for advertising those problems are as interesting for graduate or undergraduate students who don't know what to work on in their lives, but have a lot of skills and energy, kind of like making them actually excited about your problems.
That is comforting to hear that there is a trend that people are getting interested in this. Karol, what do you think from your perspective in your field?
From my perspective, we have a lot of works on reducing the amount of data required to train bigger and bigger models. That's one of the trends. Other thing is that many new approaches emerged from NLP, natural language processing, to computer vision. So we are learning from others' experience, and we are improving our results in computer vision using those methods. The classical convolutional neural networks are maybe not longer state of the art in computer vision. That's surprising after years. Now we are using mostly transformer architecture from NLP, and it's interesting thing because on the last CVPR conference you could see the computer vision, the biggest conference in computer vision. You could see even work with vision transformer for gigapixel images, which was supposed to analyze medical images, pathology images, large slices, to find if it's from a patient with disease or not. Yeah. So the trends are that we are creating larger models, working on larger data, and we are working on requiring less annotations, like less samples, few-shot learning, zero-shot learning even. But this is still work in progress. And here in this particular problem, we should focus on finding similarities, and that's I think the interesting current direction of the community. And as Łukasz said, I also think that we need to somehow merge disciplines to let's say to have new directions, new research. Yeah.
Yeah, I agree. I see that trend in a lot of fields, actually, even in astrophysics or math or computing in general. That there are people, like I said, with narrow specializations, which are very necessary, and they don't really communicate with each other. I mean, you do some state of the art, you do some paper, and you develop something, and someone else does some extraordinary tools, which, you know, they could communicate and use that. So probably we have to all get in one room at some point and talk like for 24 hours, do a adult hackathon or something, and maybe we'll get there. All right, so I see we have a great deal of new developments and some problems. That's science for you, I guess. But I'd like to go now around the room and ask you to please tell us about one important thing you haven't yet mentioned, but you think it's important to do so today when you have the floor, and maybe encourage people to, oh, I've made this development, so please can someone take care of it, because this is where my specialty ends. So Eva, you start.
Let me think. So what I would say, it's maybe that modeling is very important nowadays and in the future. Machine learning, for sure, in this kind of research, especially biosignatures.
What would you need? I mean, you go to work tomorrow and you don't have some tools. What would you say? I need this. Make this for me. What would you say? It's something that's lacking.
I would say that I would like to fly there, take the samples, come back and check it in the lab, because I think that this is mostly probable that we can check it for sure for 100% on Earth, because now it's very complicated. Even if we are sending some tools there to create some special, I don't know, for example, chromatography, yes, like still it's, it is on rovers, yes, but still it is not that complete what we have on Earth. So I think till we have no samples from that places, it's really difficult to assess and what we want to see, for example, inside the rocks, especially inside the rocks, it's very complicated.
Yeah, I can imagine. At least we have some samples on Earth, like volcanoes and all those patterns we talked about a lot of times. Yeah, we can look for that.
Exactly. So we can compare like to every rocks, yes, and we can't compare it to the rocks on Mars. for example. It's very simple. Maybe from the moon it will be nowadays it will be better, but not yet from Mars.
Yeah, let's hope in the near future then.
Yeah.
Janos, how about you? What would you say? Like, do you have anything that you really want to add today, or maybe you would like to complain about something you don't have?
Oh, I never complain. I never complain. We live in a wonderful time when we are going to have more data, and then we are going to outsource this data to other people who know what to do with this. Yes, like Łukasz and Karol. But what I really would like to say, or as it is now often called, raise awareness, is the communication. Yes, because what machine learning and artificial intelligence crowd or scientists or engineers have is a wondrous collection of methods. Yes, and they often do not have projects that those methods are immediately applicable to. So I hope that this panel is sort of, maybe somebody will have an idea how to connect this and how to facilitate this communication between those two worlds. Because, for example, I'm an astrobiologist. I know many different sciences, from biology to physics to chemistry but I have no information and no knowledge about machine learning and artificial intelligence. And that's kind of expected. It is a very common situation that scientists do not have this information how they can apply these methods. But we know that we probably could, but we do not really know exactly how. And on the other hand, the engineers in machine learning do not really often have the immediate idea what could those wonderful methods be applicable to. So today we gave you just a little bit of examples, like, for example, the spectra from various different planets that hopefully we are going to soon have in Plentitude. But there are many others. And because astrobiology is a syncretic science, where basically every science comes together to actually get us results. And I really hope that this is going to be sort of like a platform for future discussion between these novel methods in computer science and the astrobiology field, because there are some attempts to use these methods, but I think that this could be much more broader than it is now. So that's it. Thank you.
Yeah, we are still coming back to this communication problem. I mean, guys, what is this? Why? Łukasz, what would you say to your defense?
To my defense, actually, when I was at Stanford, I kind of experienced the same problem between medical field and AI, and I started a health AI working group with like 500 members and people trying to solve problems in healthcare, bring problems from healthcare. There was also, we tried to also involve entrepreneurs as a big part of it. And that's actually something that I was thinking right now and was curious, which is maybe a little controversial for a research panel. But from my own perspective, I'm kind of like on the edge of academia and industry right now through the startup that I created and then sold. And I see that there are companies like SpaceX is, of course, like the clear example of a company that kind of not only brings the new technology for exploring the universe, but also monetizes that, and that makes them able to actually produce more technology. So I'm kind of curious, and I don't have actually a question or a comment on that, but like if there were some kind of entrepreneurial paths here, so not only pure research, but like actually building those telescopes with some commercial value, or building new technologies for exploring the world with some commercial value on Earth or outside of Earth, that might, again, stimulate not only researchers in AI, but also those entrepreneurs who want to devote themselves to just build companies that bring value to the world. So I'm just curious if that's going to happen anyway.
I'm very glad. You see, there's hope. There are people like Łukasz that gather other people and make them talk. That's good. That's a step in a good direction. Karol, what would you say? Do you want to like shift the blame a little to scientists? Please don't, because I'm a scientist, but what would you say?
I hope we will have many data sets, open source data sets, and challenges, let's say, on some platforms where participants can solve real problems concerning the search for life. Yeah, if we could have such data shared somehow and defined the rules in such competitions, we could, let's say, inspire new people coming to the field to learn how to apply machine learning, deep learning, the whole artificial intelligence in this field. Yeah, so it could be beneficial for training new generations of people working in astrobiology or let's say maybe AI astrobiology or something. Yeah, so we could somehow get this knowledge to those people. Yeah.
Okay, so I see it this way. Scientists, please do share your data, share your developments, not only in these small journals or scientific papers, but do reach out to students, to other companies, and make them aware that there's stuff to be discovered and methods that you could use you would want to apply. And engineers, please look around. Don't only do models. See where you could apply them. Like, oh, there's this whole field of medicine. Maybe I will try to apply my methods there. So, okay, after this wonderful match, I think we can go to questions because there are a lot of them. So let's choose some. Oh, this one is interesting. So, can AI be used to navigate a spaceship or a rover? What are the kinds of input data for that? Who would want to answer that? Who takes the challenge?
Yeah, I actually, I will be happy to answer, since I kind of tried to answer it briefly earlier, or talk about that. So now a big trend in robotics is reinforcement learning, for sure. And the idea is that basically we model the environment where a robot is supposed to navigate, and we build a control by just trial and error interaction with this environment in many times. And we do that by kind of modeling the control with a massive neural network. And now with lots of experiments in this modeled world, we can collect tons of data and train the model without actually real data. So just using this artificial simulated data. It requires a good model of the environment that we're supposed to navigate in, like Mars or some other planet in this case, but that's relatively maybe not easy, but doable. So right now, one of the coolest approaches and like mostly explored is reinforcement learning. Pure reinforcement learning didn't really work out, and like people tried to use some more sophisticated models. But yeah, I would look into this path and maybe not tell you too much in this short panel here.
Okay. Thank you. And we have another question. I think it's two-part question, and I think it goes for Carol. So several times it has been found that AI creates its own language in areas where researchers did not expect it. And if AI can create something beyond our control, what level of confidence can we have in its work?
Oh, it's more marketing than the real problem, which was mentioned. Let's say if you follow recent advancements, OpenAI just shared their ChatGPT model, large language model, which is model with you can use to chat, to just ask some questions. Let's say even prepare, let's say, whole blog posts about multiple topics in multiple languages. Yeah, and that's this particular problem of developing the new language by a model was just, let's say, media exaggeration. Yeah, so it's not the real problem, but we still need to understand what models learned from the data. We don't know it exactly, and that's the real problem, understanding how the model works. And this is the whole trend, explainable AI, which is recently pretty much important, especially in medical data, where we want to know about what was the reason of choosing the decision by the model. Yeah, so the model need to specify that it focused on, let's say, some interesting part of the image, and it was important part. Yeah.
Yeah, I agree. And another question for the AI team, you're popular today. Is there a physical limit to how much we can reduce the input data for AI? Interesting question. I want to know too.
I can try maybe to answer, because because we can use the AI on the, let's say, on the platform to compress the data. Yeah, so newest compression methods use deep learning models which are trained on large data sets to provide this short vector representation of the image, which can be sent and then decompressed using the rest of the model, yeah, which decompress the data. So we can reduce the size of the inputs, and the bigger problem is the number of let's say examples, yeah, which we can reduce using self-supervised methods. Yeah, so we can train the model on a task. Let's say we mask some parts of the image, and model need to predict what is in this masked part, the part of the image. And using such a training, we don't need to label the data manually. Yeah, it is done automatically in the training. And as a result, we have a model which knows the data. Yeah, it was looking at all the examples multiple times, and then we can reduce the number of examples to train the final model for our task.
Okay, thank you. Łukasz, you want to add something to that, or do you think that exhausted the question?
Just one comment is that actually this GPT example that Karol mentioned earlier of a language model that covered like most of the stuff that is on the internet as a training data is a model that could be seen as something that doesn't need more data to learn something new. So like you could use it to actually extract key features from a new type of data very easily. So if you pre-train a model with a lot of data, then for training it for some new task, you actually may get to as low as one or several samples to have something useful from it.
Okay, thank you. This is not a question, but I'm going to transform it as a question. And the second thing, if only AI can process such large databases, then only AI can check the results of search itself. We are only recipients. So what, Eva and Łukasz, what do you think about that? How sure can we be? I mean, if we don't know what life is, we are only looking for anomalies. How can we be sure? Do we have models, or do we have like a threshold? How does that look?
So actually, I think it is a very big problem, because if we have a lot of data, I'm not modeling, but I think that as much as data we have, it's a problematic, because, for example, for me, if I would like to assess, for example, aerosols, yes, and compare it to aerosols on Venus, on Earth, I have many data, really, because it depends on actually climatology, about the features of the ocean, about the features of the, for example, the composition of the aerosols on Earth. So data which we have from Venus, for example, it's not that much as we have on Earth. So what is the problem here between it? We can't compare it actually. I don't know if I understand good, but in the modeling, it's a big problem if we have a lot of data.
Is it a big problem?
For inference, I could agree that whenever we want to understand the world, using a model, and having a model like F equals MA was much easier than having a model with millions of parameters. And now if in F equals MA, we could interpret parameters and have measurements, have prediction from it, and everyone knew what's happening. Now we have kind of similar idea of models, just an equation, but like an equation with millions of parameters, and we don't know what those parameters mean. And right, like interpreting it is difficult, but we are getting to the point that it might not be really possible. Like the world is actually more complex than F equals ma, as it was shown by Einstein, and like it will be shown more and more that like we're able to model very simple things, relatively simple things that a human brain can actually understand, and we see that those more complex models are actually better. So that means that actually the world might be more complex than we are able to understand. So yeah, like I'm not that hopeful in explaining everything, but we can still use those models for our advantage. That's still nice.
Yeah, that's a very good point. You don't have to have an exact function that replicates what is actually going on in details. You just want like a general idea of what's going on. This is what I actually was the most important thing I think I have from physics undergrad, which was everything is just an approximation, and that's okay. So yeah, I agree. So we have another question. How much data bias there is in AI sets and training objectives, and how much they can influence the search for life? It's somewhat connected to what we already discussed, I think.
To answer how much bias we have, we should, let's say, prepare somehow tools to measure the bias in the data set. Yes, and in such application, we will have a real problem with the bias because of the amount of data. Let's say all the data will be 99.9% or more nines after the decimal point. There will be no life at those samples. Yeah, so we can assume, let's say, it will be 100% data without the life. So it will be pretty much hard to somehow process it. But as we said, we can, let's say, use AI to speed up the process, because I think still we need humans there in the process. But we can use AI as a tool, yeah, to reduce the number of samples we need to check. Yeah, so we can use AI to somehow group those samples and reduce the human effort, yeah, in such process.
Yeah, that is a good point. I mean, Janusz, okay, so you lead a big project. Say you have some results that says there perhaps is a life there. How would you actually check that? Because we all know how peer review works, right? So.
Well, science is a self-correcting phenomenon. Yes, so eventually we are going to get to the truth. But yeah, there will be. It's hard to say what are going to be our biases. We just have to go there and make measurements, and then we are going to make interpretation. What is quite important is that where I, for example, see the AI to be extremely useful is some sort of on-the-fly AI analysis of what data we should send back. Because what is quite important, for example, is that when we design space missions, for example, we are always limited by the data that we can send back to Earth. So, for example, having a new algorithms or new machine learning methods that would tell us which data to discard and which to keep ahead of sending them back to Earth, because we do not want to waste our allocated data that we can send for something that is not really important. And we live in an era when we are going to collect more data than we can actually logistically will be able to send back. So this sort of decision tree, how to decide what is important and what is not important, is something that is extremely important. That is something that is going to be very useful for us. And this is also where this sort of overlapping platform between these two fields could come to the forefront. This is essentially one of the ideas where I see it.
Yeah, I completely agree. I mean, we need to set some sort of a threshold, how to decide which one of them we should check by ourselves, which one of them we should even send. Yeah, I agree with that. We have a lot of questions, but I'm only going to choose one or two because we're already over supposed to be, but interesting questions. So What are the biggest problems and limitations that currently accompany the use of artificial intelligence in space exploration? Because we mentioned already that the communication, but do you find that there is something else?
Well, I think that the communication is the main problem, because there is no limit. The space exploration itself doesn't have a limit. The universe is infinite, as far as we know, of course. Yes. And the methods that the machine learning and artificial intelligence community are developing have phenomenally broad applications. We just have to start speaking the same language so we can understand each other and find this common ground. And once that happens, there is essentially no limits to where the artificial intelligence or the machine learning could be applied. I already mentioned this sort of decision tree on which data is important, which data is not important, as a very basic but very important example of such collaboration that could happen. But there are, of course, many more.
Okay. I would just add that.
Go ahead.
That's actually an excellent example. Like, as a machine learning engineer, AI engineer, I wouldn't think that one of the limitations is the amount of data you have on this rover. Once Janusz mentioned that, it's quite obvious that of course we have this constraint, but like, that's not something that comes to your mind as a researcher. Like, we have data centers of Google that can process everything, and now you're constrained, and if you don't know those constraints, you won't come up with the solutions or methods useful for this specific field. So and that's, this intersection is where the interesting problems can come up, because like with infinite compute resources, you can come up with great models, but now you're constrained with what Janusz mentioned, that there are tons of other constraints. And now how can you find a solution here? So yeah, it's again communication, but this example is very nice, actually.
Okay, thank you. 2 last questions and we are done, I promise. So can we use AI analysis in situ, for example, somewhere far away, or it demands a lot of power supply, too much for a small device? How does it work now?
So one branch of AI research is deployment models in, let's say, low power setups, such as mobile phones, which are, let's say, one of the lowest energy devices, which uses AI models on the daily basis, massively, Another thing is embedded computing, which supports, of course, running deep learning models. But as I know, in space there are many other problems, such as the special CPUs, redundant CPUs for computations, and I think that could be the problem.
Okay. So our last question today is, can anyone define what neuromorphic algorithms are used for and how they differ from neural networks? Have you guys ever encountered that?
No, I'm checking now what it is, but probably won't.
Me neither. That's why I'm asking. What is neuromorphic algorithm? I mean, I can probably guess, but not.
We would have to apply machine learning methods to figure out what it is, unless Google immediately finds us an answer.
Yes, yeah, and then run it through a peer review to confirm. Okay, guys, thank you for that excellent discussion. It was really stimulating and fascinating. And now we all better understand what astrobiology and the potential of AI usage is. So I urge you all to communicate, really, because this is the main thing we can all take from that. So a huge thank you for being here to both our guests and the audience. And thank you for this inspiring and informative discussion. I hope I will see you all again. And we will see each other and communicate more, I guess. So let's get back to the conference and enjoy other panels and discussion and sessions. So thank you and goodbye.
Thank you so much.
Thank you. Bye.
Thank you.